So today we're going to talk about modular arithmetic. Modular arithmetic is for doing these arithmetic operations on a finite set of numbers, the numbers from 0 to n minus 1, where n is some alphabet size. So the goal ultimately is to describe cryptosystems, particularly what's called the RSA cryptosystem. That stands for Ravesh, Shamir, and Edelman, who came up with this method. What you need to do is take a message and encode it as a sequence of symbols. And these symbols will come from some finite alphabet, let's say of size n. Remember how you encrypt a message, or how you might think to encrypt a message, is to take those symbols, convert them to other symbols, so that now the message can't be understood, and then the receiver knows how to decrypt it by converting the symbols back to their original form. Right? That's how you would hide a message over a public channel. We're actually going to do that using arithmetic operations on these symbols, which are actually going to be just the numbers from 0 to n minus 1, this finite set. So we're going to have to learn how to do this arithmetic, like addition, multiplication, exponentiation, because those are going to be the operations used for both encryption and decryption of private messages that you don't want to be spied upon. But first we have to learn how to do these type of arithmetic and the algorithms we use to do these operations, and also consider the running time of these algorithms. So the important thing to know about modular arithmetic is that you can take any integer x and consider it modulo some positive integer n. So when we write x mod n, what we mean is you should take x and consider the remainder when you divide x by n. Right? So when you take x and look at the remainder when divided by n, that should be a number from 0 to n minus 1. So if you recall from grade school or high school, for any n bigger than 0, you can always take an integer x and write it as some integer multiple of n plus some remainder r. And that's where the remainder r is a number from 0 to n minus 1. And that can be done uniquely for any x and any integer x and positive integer n. You can always write x as some multiple of n plus a remainder r, plus some positive remainder r. Right? So we might say, for example, that n goes into x q many times with a remainder of r. Okay, let's do an example. The number 37 mod 5, right? That equals 2. That's 2. And I can write 37 equals 7 times 5 plus 2. Notice 2 is the remainder here, right? So this is, of course, the thing that I'm interested in when you take something modulo. You actually don't really care about the fact that it's 7 times 5. You throw away the 7, the multiple of n in this case, and you just look at the remainder. Similarly, 5 mod 7 just equals 5, because 5 is smaller than 7, so the remainder upon dividing by 7 is just 5. When you look at the integers modulo n for some n, this gives you some equivalence relation between integers that we didn't have before. We call this congruence modulo n. So take any integers x and y. We can say that x and y are congruent mod n if they have the same remainder when they are divided by n. Now, this is useful for a number of reasons, but what it lets us do is it lets us consider the integers, the infinite number of integers, and break them into just n many buckets. So for example, if we take the integers modulo 3, we get the bucket of what you might call all the numbers that are 0, that are congruent to 0 mod 3, which is this first bucket, right? All of the integers which are congruent to 1 mod 3, which is the second bucket, and then all the integers which are congruent to 2 mod 3, right, which is this third bucket. Right? So we've taken an infinite number of integers, and we've said actually anything that has the same remainder upon division by 3 is going to be considered equivalent or congruent in part of the same bucket of integers. So it's useful to consider some basic facts about this congruence modulo n relationship. So assume that we have x being congruent to x prime mod n and y congruent to y prime mod n. Okay, just let that be true. Then two facts are true. One, we know that x plus y is going to be congruent to x prime plus y prime mod n, right? So you have, if you have x congruent to x prime and y congruent to y prime mod n, then adding them together makes the sum still congruent to x prime plus y prime mod n. It's just a useful fact. Similarly, x times y is congruent to x prime times y prime mod n, right? Multiplication, this congruence modulo n property holds true when you multiply numbers that are congruent. So these two facts are actually useful to help us compute things in modular arithmetic. Let's consider an example. I want to figure out what is 2 to the 345 mod 31. So 2 to the 345 mod 31. That seems a little bit annoying to compute because I'd have to raise 2 to a very large power first and then take the remainder upon dividing by 31. Is there an easier way to do that? It turns out that there is. Notice that 345 equals, well, that's 5 times 6, 9, right? And now I'm going to use this fact. It's actually very helpful. So 2 to the 345 also equals 2 to the 5, right? I can first do the 5 exponent, then to the 6, 9. And, okay, what's 2 to the 5? Well, that's congruent, or that's actually congruent to, what's actually equal to, this is actually just equal to 32 to the 6, 9. And, but what is 32 mod 31, right? This is actually congruent to 1 to the 69 modulo 31. Why is that? That's true because 32 mod 31 is just 1, right? 32 mod 31 is just 1. So now I have, I can simply write 32 is congruent to 1 to the 69. But of course, 1 to the 69 is easy to compute, right? 169 is just equal to 1, and that is congruent to 1 mod 31. So you notice that I saved a lot of time by using the above tricks to simplify this computation. Just a little side note, the word of the day is koala. It's not actually clear why I needed this white piece of paper, but anyway. So now let's talk about multiplicative inverses in modular arithmetic. There's this question, which is, I've so far talked about addition of numbers modulo n. I've talked about multiplication. Subtraction is also pretty straightforward. But what about division? What does it mean to divide two numbers in this modular arithmetic framework? Can I take 3 divided by 5 mod 7? Does that make sense? I mean, isn't 3 over 5 a fraction? What does 1 over 5 mean mod 7? And you think that since I've been talking about how we're working with the integers 0 through n minus 1, that it wouldn't make sense to talk about fractions. But in fact, it actually does make sense in certain cases. We actually can talk about multiplicative inverses. So what do we mean by a multiplicative inverse? Like when we're talking about fractions, you know, we can say, you know, in the real numbers. So when working with real numbers, not in you know, the numbers, the integers modulo n, but in the real numbers, 1/5 is the multiplicative inverse of 5 because 1/5 times 5 equals 1, right? So like with fractions, we can say, you know, the real numbers, we can say 1/5 is equal to the multiplicative inverse of 5 because when I take 5 times 1/5, I get the number 1, right? The key thing is that I get this number 1, which is, you know, the thing I'm trying to get back to. So what about in modular arithmetic? Well, it turns out that, that 3 is the multiplicative inverse of 5 mod 7, right? It's a multiplicative inverse of 5 mod 7. Why is that? Because notice that 5 times 3 is congruent to 15. It's actually equal to 15, which is congruent to 1 mod 7. So you notice here that I took 3 times 5, and I got 1. So somehow you can think of 3 as the multiplicative inverse of the number 5. So here's a precise definition. We can say that z, the quantity z, is the multiplicative inverse of a modulo n if a times z is congruent to 1 modulo n, right? And we often denote this as z equals a inverse modulo n, right? That's the notation we use. We can say that a inverse is z in this case, because if you multiply z times a, you get 1 mod n. So here's a good question. Does a multiplicative inverse always exist? Can we always take the inverse of a number, mod n? Turns out the answer is no. Let's look at a good example. Notice that 5 inverse mod 6, right? How do I find an inverse mod 6? Well, it turns out that that equals 5. Why? Because take 5 times 5. 5 times 5 is 25. That's 1 modulo 6, because 6 times 4 is 24, and 25 is therefore 1 modulo 6, right? But what about 2 inverse mod 6? It turns out that that doesn't exist. Does not exist. If you try to find a number that you can multiply times 2 mod 6, you'll never find anything that equals 1 mod 6. And it's kind of easy to see why this is true for mod 6, because anything you multiply 2 times is going to be an even number. But to get something that is 1 modulo 6, to have a remainder of 1 upon dividing by 6, that number is going to have to be odd. So there's no way to find a number you can multiply by 2 to get something that is 1 modulo 6. Again, because you would have to get an odd number, but anything times 2 is going to be an even number. That's not going to be possible. Is there a general rule here? It turns out that there is. Okay, so the theorem here that is relevant, and I won't prove it, but I'll just state it, and you can check this on your own time if you like as an exercise, is that you can take a multiplicative inverse, modulo n, if and only if a and n are relatively prime, or another way to say that is that the greatest common divisor of n and a is 1. That means that n and a don't have any multiplicative factors in common other than 1. So we notice that 5 does have a multiplicative inverse, mod 6, right? Because the multiplicative inverse of 5 is 5 itself. But we notice that 2 does not have a multiplicative inverse, mod 6. Why? Because 2 and 6 have a common factor, and that's 2, right? 2 divides both 6 and 2. 5 and 6 do not have a common factor. No other integers other than 1 divides 5 and 6 together. So far we've only been talking about the basics behind how to do modular arithmetic, addition, subtraction, multiplication, and some of the questions of when you can take multiplicative inverses, etc. One thing we haven't talked about is the actual algorithms we can use to compute these things, and that's what we're going to do in our next video. So sit tight.